just as you never really understand an algorithm in programming until you code it up yourself, one can never really understand a piece of mathematics until you've proven properties about it. So let's try to prove one result that we can figure out just from the definitions of sine and cosine that I gave. So here's the statement of the theorem. I claim that if you give me any angle theta, so remember we use this Greek letter theta to represent angles, and it's a real number, so any real theta, there's this property that if you take the sine of theta and square it, and then take the cosine of theta and square that, and add them together, you will always get 1. Okay, so this might seem slightly mysterious to begin with, but let's begin the exploration to see if we can figure out why this might be true. Okay, so why don't we test some cases. So we've already computed a few values, that's a bad M, a few values of these sine and cosine. So let's try, for instance, 0 degrees. Alright, so we saw that on the circle. That's the point at 0 degrees is right here, this point on the x-axis. So that has x-coordinate 1 and y-coordinate 0. So if we have sine of 0 squared plus cosine of 0 squared, with parentheses, well, we know that sine of 0 is that y-coordinate, so this, maybe I should use a different color. This will be 0, and cosine is the x-coordinate, which is 1. So we have 0 squared plus 1 squared equals 1. And I'll go back to pink, equals 1. Okay, so the statement of the theorem is true in this case when we let theta equal 0. What if we try 45 degrees? Well, we figured out sine of 45 degrees. Well, maybe I'll write the sine again. So sine 45 degrees, which we found on the previous slide. So sine 45 degrees squared plus cosine of 45 degrees squared. Then what's that going to, I should scroll. What's this going to be? Well, we saw by using that 30, 60, 90 triangle trick on the previous slide that sine of 45 degrees is 1 divided by square root of 2. And cosine of 45 degrees is also 1 over square root of 2. So if we square these, if I square 1 over square root of 2, I get a half. And if I square it again and add it, I'll get another half. So when I add those together, I get a half plus a half, which equals 1. Okay, I'm starting to believe this is true, but let's try one more. So we saw this 30 degrees. So this would be sine of 30 degrees, which we saw was 1/2 squared plus cosine of 30 degrees squared. And what are these guys? Well, we figured out that the cosine of 30 degrees was this weird square root of 3 divided by 2. And the sine of 30 degrees was 1/2. So when we add those together, after squaring them, you square 1/2 and you get 1/4. You square root 3 over 2 and get 3 over 4. So 1/4 plus 3/4 again equals 1. Okay, so we're starting to see that this pattern might be true for all angles. And let's just draw one more picture to see if we could get some intuition for how that would be true that we can rigorize in the proof. So, oops, I'll draw our circle again. So remember that the key of all of these trigonometric functions is that they're labeling points on the circle. That's really the definition. So if we just pick any angle theta, so this is any angle theta, and drop this triangle, we know that the radius of this circle is 1, and we know that this x, this is the x length, so this is cosine of theta, and this vertical part, which I should draw a little more carefully, so this vertical height, this is sine theta. So maybe now it's becoming a bit clearer. Maybe I'll make it just one more hint to see how this will be converted into a proof. So what are the coordinates of this point? Well, the xy coordinates are simply cos theta, sine theta. This is a point on the unit circle. So now we're starting to see why this is true in general, because cosine theta and sine theta are the x and y coordinates of a point on a circle of radius 1. But we remember the equation of a circle of radius 1 is x squared plus y squared equals 1, right? Or 1 squared, the radius squared. So if cosine is the x-coordinate and sine is the y-coordinate, it looks like if that coordinate labels a point on this circle, this equation will always be true, that x squared plus y squared equals 1. So that's just from the definition of a circle. A circle is the set of all points x and y such that x squared plus y squared equals the radius squared, which is here 1. So that, I think, should be enough exploration. Now we see how to understand why this statement is true. And I will show you now the argument, which will be kind of the polished version of this. So I've written it out already because I'm very bad at talking and writing at the same time. So this will be our argument. I'll just walk you through it quickly. So at the beginning we assume theta is any real number, so let theta be in R. Now we're going to remember the definitions I gave in the first video. Those were the definitions of sine and cosine, where sine is the y-coordinate of a point at a given angle theta on the unit circle. Cosine is the x-coordinate. So I'm just going to say that here. By the definitions of sine and cosine, we have that cosine theta is the x-coordinate of a point on the unit circle, or also known as the circle of radius 1. And sine theta is the y-coordinate of that same point. Now I'm just going to rigorize what we said in the exploration part about the definition of a circle. So this is where we use the definition of a circle. A circle of radius 1 is defined as the set of all points x and y that satisfy this property, x squared plus y squared equals 1 squared, which of course is the same as 1. So here I appeal to the definition. And then finally we just conclude the proof by saying that, okay, if cosine theta, as we've said, is the x-coordinate of some point on that circle, and sine theta is the y-coordinate, then those must satisfy the definition of a circle, which means cosine theta quantity squared plus sine theta quantity squared equals 1. And this is sometimes called the Pythagorean identity for trigonometric functions, because another way to see it is just using the Pythagorean theorem. If you make that triangle, the x leg has length cosine theta, the y leg has length sine theta, and the hypotenuse has length 1. So you just do leg squared plus leg squared equals hypotenuse squared and get the same result. But I actually prefer this proof because I think it's cleaner just to use the definition of a circle, because it emphasizes that trigonometry is at heart really about the circle, and the triangles are something of an afterthought. Good, so that's our first actual proof about this. To review what we spoke about in the first video, I defined sine and cosine on the circle as the x and y and x coordinates of a point at angle theta. In the second video, we wrote down a few values of sine and cosine for common angles, 30 degrees, 45 degrees, and 60 degrees. And then in this video, we proved this very important identity, the Pythagorean identity, cosine of theta quantity squared plus sine theta quantity squared equals 1. Good. So this, I think, is enough for our first introduction to trigonometry. I will post these on Piazza and put some challenges along with them so you can test how well you've understood.